force is a vector, right? We were saying now, if the force as a vector is conservative force, it will be written as the gradient of a scalar function. This scalar function, we call it potential energy, okay? And we put a sign, this is the sign convention that dynamicists agree to, is that the force is not phi is the negative of that. It's as if this function is negative v, okay? So a conservative force is a vector that can be written as the gradient of a scalar function. That is, its x component, the x component of the force is simply derivative of v, your potential energy with respect to x. The y component of the force is the derivative of your potential energy with respect to y, and so and so. Okay? If this is the case, you can see immediately from these things that the work done, which is the integral of f dot dr between any 2 points, is path independent for conservative forces, and simply equal the change of this function. Since we have negative, so it's negative the change of potential energy V1 minus V2. Any question about that? And is path independent. So this is what of the properties that these forces exhibit or possess. In particular, gravity is a conservative force. So the work done by gravity has nothing to do with the path. If you go from point 1 to point 2 along this line, I don't care, it's simply the mg h, right? If you go right straight, okay, it's the same quantity, I don't care about the path. Okay? The work done by conservative force is path independent, is simply the change of the potential energy between the 2 points. Any question?
Excuse me, why we have the negative sign?
This is, like I said, it's just a convention. Dynamicists agree that the force is the negative of this thing. Probably because it started with gravity, and I'll show you some examples of the conservative force. For gravity, the force is kind of force like this. A mass and another mass, the gravitational force on this guy is negative to the center. Yes, please.
You say that it's always true. It's also what it means that it's for conservative and non-conservative.
This is very good. This is what is always true. This is what is for only conservative forces. Okay?
So you're using this to explain your rule?
No. This is always true. And this is a good point because we're going to come back to it. Okay? This rule is general. The change in kinetic energy equal the work done is general. But now if you substitute the work done from there as the negative change in potential, if you're saying change in kinetic equals negative change in potential, this is for conservative forces only. Okay? We're going to come back to it. Yeah. But first I need to give you some examples of conservative forces from nature. Any question? Examples of conservative forces. First, gravity. The potential is simply mg in the y direction if you consider the y as the elevation. So the higher the y, the larger the potential energy. So potential energy is an energy due to position. You have a good position, you have higher energy. So since this is your potential energy, remember if we differentiate with respect to x, you get the force in the x direction, obviously you get nothing. Differentiate with respect to y and put negative sign on it, this is the force. It's simply negative mg in the g direction, correct? So gravity is just straight downward, and this is the associated potential energy. Spring force, the potential potential energy is 1/2 kx squared. It's only function of x, so you get force in the x direction only. So it is, you differentiate with respect to x, you get kx, and we have our negative sign, so negative kx in the x direction. Right? What else? Gravitational. V is negative m g m over r. So it's just a function of r, the radial position. So you get the corresponding force as in only the r direction. Conjugate with respect to r, you get 1 over r squared in positive, and we have g m over r squared. In the r direction, we have our negative. We have the Coulomb, the electrical force. Very similar. The potential energy is K, Q, Q's here are charges, right? Over R, and you get the force the same in only the R direction. These are types of conservative forces. In nature, if you have a generic force, if I'm just pushing this disk by an applied force, the default is that it's a non-conservative force. So this is the default. The special case is the conservative force. Okay? Yes, Joseph?
Are there any potential? Are there any kinds of potential energy that are not conservative?
What do you mean conservative? What do you mean not potential energy not conservative?
Also, these are examples of conservative forces.
Conservative forces
Okay.
is a force. Conservative force is a force that can be written as the gradient of a scalar function, and we call this scalar function like this as a potential. So
Okay.
the existence of a potential energy per se guarantees that the associated force is a conservative force.
Okay.
Okay? Otherwise, we will not call it potential energy.
Because the potential wouldn't exist then.
Yes, correct. Any question, please? Any question? Okay, so like I said, this is always true. Now, for conservative forces only, for conservative forces only, delta T is equal to, I'm going to substitute the work done by negative the change in potential energy, because it's a conservative force like we had from before, which means that delta T plus delta V, the change in kinetic plus change in potential. Change in kinetic plus change in potential, what's this? This is the change in the total energy. This is 0. So it's not surprising that for conservative forces, the energy, the total energy is conserved. Okay? Obviously, this is for conservative forces only. Please don't confuse this with that rule. Okay? Any question? Because we usually teach them together, in undergrad and grad, so people, when they get it together, they think that this rule is applicable only to conservative forces. This is not the case. Any question? Okay. A few minutes. Don't panic, we'll not have a quiz today. But we'll add one more quantity. Any question? Any question, please? Types of non-conservative forces. This is before leaving. What's the most common non-conservative force?
Friction.
Friction, right? Yes, friction of course is a non-conservative force. Okay, if you do the line integral of friction dotted with your distance along this path is different from that path, different from this path. Types of friction we have the drag on higher units number things. It's the drag force, like airplanes, simply some coefficient C. It's in the negative direction of the velocity and it's quadratic on velocity. So this should be V squared. But we write it absolute value V times V as a vector to indicate that it's in the negative direction of the velocity, of course. This is like airplanes. And for low speed things, low units number medium, actually it's the friction force or the drag is linear in velocity. Negative C times V. Okay? And we also have the column friction. That we deal with. These friction forces or drag forces are when you move in a fluid. Okay? But if you move on a surface, we have the column friction, F friction. Simply negative mu times F, the coefficient of friction, times the normal force in the direction of the velocity, or in the negative direction of the velocity. So I need the direction of the velocity here. So I'm going to have the velocity vector divided by its magnitude to get just the direction, and it's the negative of that. What's this mu? I'm just reviewing things. You should have seen these things before. What's this mu? It's the coefficient of friction. And it is here, we have this very common diagram between the applied load and F of friction, the magnitude. So when you're moving some object, applying some load, and you have F friction here resisting you, you need to apply enough load to overcome the friction, right? So you apply more load. The issue is that the friction does not stay the same, actually increases with your applied load. Here is the curve, right? So the more applied load, the more friction. You apply more, friction increases until you just beat it at some point. This point we say the coefficient of friction, at this point we call it the static friction. Let me write it in green, to be obvious. At this point, if friction is equal negative mu in the opposite of the velocity, this mu will be the static friction. Once you beat this value of the static friction, luckily, actually, the friction force decreases, drops immediately. So once you apply more force than the static friction, okay, you beat the friction, so you're gonna move. Once you start to move, now in motion, the coefficient of friction is different. We call it kinematic friction. And luckily, the kinematic friction is less than the static friction. You apply load, the friction is there resisting you. You apply more, the friction increases. Apply more, the friction increases until you overcome the static friction and you start to move. Once you immediately move, then the friction becomes less because now you're resisted by the kinematic friction. So as you all know, it's easier to push a moving object than static object, right? So these are types of non-conservative loads, and we're done today. Like I said, there is homework we do in a week. Sorry, before you leave, folks, I assume that you managed to see the Dropbox. It's not a website, it's a Dropbox. Dropbox for the course on EEE, not a website. It has the slides of the first lecture, it has the syllabus, and I will upload the homework on it today.